So this is about grid covering problems, and I'll introduce what they are and talk about some history, but also a few recent results. And I don't have that many slides, so please stop me in between and ask a lot of questions so that we can actually fill up the time for this seminar. Okay, so this is joint work with various people and their names will appear throughout the talk. Cool, let's begin. So what exactly are we talking about? So say we have this grid of points. We have these 12 points in the plane. And let's say I want to cover all of these points by straight lines. So what's the minimum number of lines required? It's not a rhetorical question. Yeah, if anyone has an answer, you can just say it in the chat. Yeah.
3.
Yeah, it's 3. Yeah, perfect. So that's pretty straightforward. You can do it with 3. And you can, it's kind of easy just by some sort of accounting. You can prove that 3 is indeed the minimum here, right? Now, just a slight variation of this grid covering problem somehow becomes a bit more challenging. So say there's this red point over there, which you are not allowed to touch with any of those lines. And now, how many lines do you need? What's the minimum number? 5. There is a guess or maybe even a proof, who knows? But can anyone do better than 5? Doesn't look like it, at least not immediately. And there are good reasons for that. So 5 can be done in this way, right? You can take these 3 vertical lines and 2 horizontal lines, and that gives you 5 lines with the required properties. You can do it in a different way, like this as well. So this is again 5 lines, right, for covering these points. But somehow proving that 5 is indeed the minimum is much harder than the previous problem. So previously you could just do some sort of accounting. And here also, like if I just give you this small example, you can do it with a computer, in fact. But in general, solving this problem where you're not allowed to touch one point requires us to use some algebraic methods. So in fact, the only known general proof of these bounds basically are as follows. So this is what polynomial method is about in this context. What we can do is we can write down each line as a degree 1 polynomial. Right? That's how a line is defined, by just some equation like this. And then you can multiply a bunch of these equations. So say you have k lines, and then you can multiply all of these polynomials that define these lines. Then this polynomial f has degree equal to the number of lines, and it vanishes at a point if and only if that point is covered by at least one of the lines, right? And then you can completely forget about the geometrical problem and just try to solve the algebraic problem, which asks for a lower bound on the degree of a polynomial that vanishes everywhere except for one point where it does not vanish. And in fact, you can prove such an algebraic thing. So let's say you can show that for every polynomial, if f of x is 0 for every point except 1, where it's non-zero, then the degree is indeed at least this m minus 1 plus n minus 1, which is how you can get the previous bound of 5. And this generalizes to higher dimensions. So in higher dimensions, instead of lines, you have hyperplanes, and a degree 1 polynomial corresponds to an affine hyperplane. And then there's this very general, amazing result of Alon and Furedi, which says that the minimum number of hyperplanes required to cover all points of a grid, of a finite grid of points, while missing one point, so here it's this one point that's missing, is at least what you expect it to be. Like the most obvious construction that you can think of by using these axis parallel hyperplanes, that's somehow the best construction. As in not necessarily unique, as we saw before, but it's still one of the best, in fact, in terms of the sizes. And this is proved using polynomials. There is an algebraic way of proving it. And in fact, now there are many polynomial method proofs of the same result. Okay, so that's the kind of grid covering problems I'll be talking about. And just to give some motivation and also some history of this. So it's not just some isolated, nice combinatorial problem. There's nothing wrong with that. We can, of course, study nice, cute combinatorial problems without any connection. But this one is pretty well connected to many other things. So in finite, yeah. Does anyone have a question so far? No, okay. So in finite geometry, which is one of my research areas, there's this notion of a blocking set, which is, if you are familiar with vertex covers in graphs and hypergraphs, that's kind of what it is. And that's the context where, in fact, this result of Alon and Furedi was originally proved for a special case. So this result is over every field. But if you think of F if you just take F to be a finite field and all your sets to be equal to that finite field, so your grid is the whole space. In that case, this result already appears in this 1978 paper of Andres Brouwer and Lex Schreiber in the context of these blocking sets, which is kind of like a dual version of the same problem. Then in coding theory, there are these very well-studied codes called Riet-Miller codes, and which actually date back to 1960s, so much older than this one, where there were some results which also, yeah, I think they imply the Alon Furedi result as well, if I remember correctly. But they were studied in a completely different language. And then in theoretical computer science, there's this whole study of polynomial identity testing, where you have things like Schwarz-Zippel lemma, and those are also connected to this result of Alon Furedi and various generalizations of that. In fact, I recommend this new paper by Gunther Rote, who's also here. So he can talk about this if I'm finished in half an hour. So then he can give the next half an hour of talk, where he describes many nice connections between this Alon Furedi result and specifically something known as combinatorial Hülster and Sards, and various results in computer science literature and also things. And something that's even more recent is extremal combinatorics. So there's this notion of hypergraph two-round numbers, and there's a very recent paper of Koltev where he uses a nice connection between these kind of polynomial problems, specifically something known as combinatorial Hülster and these hypergraph Ramsey numbers. So that's, I think, enough motivation to actually look deeper into these kind of problems. Okay, any questions so far about the motivation or something else? If not, then let's move on. Now, my talk is mostly focused on a multiplicity variation of this problem. Okay, so originally you're asked to cover every point of the grid at least once, except for this special point which you're not allowed to touch. And now let's say we have another parameter k, and we want to cover every point at least k times. If you write this down as the polynomial, like when you multiply these polynomials defining the hyperplanes, then this says that those polynomials vanish with a certain multiplicity at every point, except for one forbidden point. In this case, what can you say? Can we actually solve this problem so nicely? Can we give nice bounds or results and so on? So that's the general direction where this talk will be in. And the most general result in this direction is a statement of Ball and Serra from 2009. Actually, before stating that, yeah, I'll keep it here. Okay, cool. I'll just state it and then get back to the more obvious bound that you could prove. So in Ball-Serra, they proved that if you take any grid A1 up to AN, and let's say you arrange them in descending order of size, then the degree of this polynomial that vanishes everywhere with multiplicity at least k must be at least k times the largest thing, so the largest ai minus 1, plus the rest. So when you plug in k equal to 1, you get the Alon Furedi result. Now, this is much better than the obvious thing that you might try when you see it for the first time, is that if I give you a collection of hyperplanes satisfying this property, I can remove k minus 1 of them, and then they still cover every point at least once, right? So if you use that idea, then you get sum of ai minus 1, and then you get an additive factor of k minus 1 over here, whereas here there's a multiplicative factor of k. So this is definitely non-trivial. But then once you have such a nice lower bound, of course, the natural question is this tight? Is this ever going to be tight for any k greater than 1? Okay, any guesses on or intuition on that? What do you feel? Right? Unless you have seen my results already. Can you think of an example where this might be tight, where k is not equal to 1? Okay, we have a very quiet classroom. So yeah, just like most of the online lectures, but it's fine. Yeah, I didn't expect that you'd come up with some example immediately, but there is still like an easy-ish case, which is in fact the most well-studied case of this problem, which is the binary grid. So if I just take the binary grid, 0, 1 to the n, inside R to the n, or in fact any field, then this Ball-Serra lower bound becomes n plus k minus 1. And this is tight, not just for k equal to 1, but also k equals to 2. But okay, now I will seriously ask a question. Can you give me a construction? Can you give me a construction of n plus 1 hyperplanes that miss the origin, but they cover every point of this grid at least twice?
It's kind of a projective thing, like
in what way?
Just trying to get inspiration, whether like kind of a projective plane kind of argument works, but
yeah, I'm not sure how projective planes would work here. As in, this is about higher dimensionals, but so projective spaces, but yeah, I'm not sure how any projective intuition works. Maybe it does. I don't know. There's also something in the chat. There's a lot in the chat. Okay, nice. So just to confirm, do the AIs also count the missing point? Yes, they do. Then that's definitely there. So without loss of generality, you can assume that each of these AIs contain 0, and your origin is the missing point, right? Because you can always translate stuff and the problem stays the same. Well, kind of. Diagonal ones, like you did in the plane. Oh, that's a good intuition from Adam, that you can take some sort of diagonal hyperplanes. For n equal to 2, this is a triangle. It must generalize, I think. That's amazing. Yeah. Start with the smallest example. It does generalize, in fact. You take face of the cubes and add some diagonals. Okay, so you're going in the right direction, but I don't have too much freedom. I can only add one diagonal. If I take all the face hyperplanes, that's already n hyperplane. So I just need to add one diagonal hyperplane. And in fact, maybe I'll write it here. You can add sum of xi equal to 1. If you just add this hyperplane, which is in the chat, sum of all xi is equal to 1, then it does have the property. So n plus 1 is tight. Good. Not sure if that's projective, but there might be some other constructions as well. And now, is this tight for other values of k? Well, that's already open. As in, it's known that for some values, okay, it's not open whether this is tight or not. We'll see. It's actually far away from being tight for any other value of k, but it is open to determine the smallest number here. That's also true, what Vladimir said. Yeah. Okay, so there's a conjecture of Clifton and Huang from 2020, which says that we need at least n plus k choose 2 hyperplanes. So not n plus k, but something quadratic in k. And this is for k fixed and n large enough. In the other regime, when say n is fixed and k is large enough, it's a completely different problem. And it is kind of solved asymptotically. Now, the best lower bound in this direction is by Sauermann and Wigderson from 2021, which is n plus 2k minus 3. And that already shows that this bound is not tight. The Bol-Serra bound is not tight for any k greater than equal to 3. And this is not an easy result. Like, this is pretty hardcore stuff over there, as in it's a long paper. There's some very beautiful ideas in there, but most of those ideas are specific to this binary grid. They don't generalize that easily. And in fact, Sauermann and Wigderson, they actually solve the polynomial problem. So this n plus 2k minus 3 is the smallest degree you can have for the polynomial corresponding to your collection of hyperplanes. Or in general, if I ask you a polynomial problem, that what's the minimum degree of any arbitrary polynomial that vanishes everywhere with multiplicity k, at least k, except the origin, then this is the precise answer. But for the hyperplane covering problem, where your polynomial is just reduced into linear factors, then we don't know anything better than n plus k choose 2. So this kind of suggests that the polynomial version of the problem and the combinatorial or geometrical version of the problem, they might have different answers. It doesn't prove it because we haven't solved the conjecture yet, but it strongly suggests that these two things are different. Okay.
So sorry,
Yeah.
the polynomial bound is tight.
The polynomial bound is tight. So there are
The
polynomials
bound of the degree.
of this degree. Yeah. So this is the correct bound for the degree of the polynomial. So you can't use the polynomial method to actually improve this. That's what they show. Is that clear? Okay. So yeah, the polynomial version is tight. And then, yeah, so what can we say? Like, can there be a separation between the polynomial version and the combinatorial or geometrical version? Well, we proved a few years back, and the paper just appeared in the journal, that if you change the field, so instead of real numbers or say any characteristic zero field, if you study the exact same problem as this binary grid, but now instead of R, you have F2. So just the binary field. So now your grid is the whole space, the whole vector space. In this case, we can prove a much, much bigger lower bound. So say k is equal to 3. In this case, when k is 3, this number is just 1. And then you have a log factor. You have n plus log n, as in there's some constants lying around. Right? So even for k equal to 3, it's not n plus a constant, it's n plus something that grows with n as well. So this is very different behavior than here in the characteristic zero case, where the conjecture is that it should be n plus k choose 2. Okay, so this shows that, yeah, the answer can be actually very large compared to the polynomial method lower bound that we have. And there is this other case that you can study over f2 to the n, where you do allow the origin to be covered at most k minus 1 times. Right? That's also a natural generalization of the classical result. You're not missing the origin, but you can touch it a few times. And in this case, we actually get this n plus 2k minus 3, which appears there as well, even though there is no connection between our two techniques. So in our paper, we don't use any polynomials. We only use some combinatorial arguments. And in fact, this nice looking bound with logs exists because what we show is that this covering problem in F2 to the n is equivalent to a classical well-studied problem in coding theory. And that's automatically, this is like the Hamming bound. Automatically, that gives you this log bound. But we can't generalize our techniques to any other finite fields. So that's very exciting stuff, but still slightly old. Yeah, questions? Any questions about this?
Are you planning to say more now about your combinatorial argument?
Not for this, because I'm going to focus on the more recent stuff. So I can say a bit if you want. As in, there are no slides. There are no further slides on this paper. Yeah.
I have another question.
Yeah.
I guess for small n and k, you can work it out.
Yeah.
Like by computer. So what is the indication that
for
is
the for this one?
Sauermann-Wightson is no, it's for example for between the conjecture and the lower bound on this slide, for example.
Yeah, I'm not completely
Or
sure.
is
I
n
think,
too large to?
yeah, well, no, I think you need n to be at least just twice of k or something like that. So probably for small values, the conjecture is correct. I think Clifton did check that, and at least that's what he told me. I haven't verified the computations, but yes, you can do it with small grids. Yeah, I think the belief is that the conjecture should be correct, and that's what the small values also tell you. Yeah, but we can double check that later. Good question. In fact, all of these problems, as in we will see some sort of nice computational way of doing these things as well. But in general, yeah, you can actually compute this. It looks like an infinite problem, but it is not an infinite problem. Okay, Adam, you wanted to ask about the what sort of combinatorial arguments? We have a lot of time, so I can say.
No, I just maybe just
Yeah.
like a rough idea. What do you mean? Like, what is it? What type of tools are you using? Not more than that.
So the main tool, firstly, is this result. The first thing that we prove is like an equivalence between this problem and the standard sort of coding theoretic problem, if you know what coding theory does about these Hamming distances and Hamming walls. So what we prove that is that any such cover corresponds to a linear code with minimum distance k, I think dimension n, and length equal to the number of hyperplanes. So once we prove that, this is just the Hamming bound, as in with some calculations. And then what we try to do is just reduce everything to that. So these arguments are kind of, there is some inductive argument there, like we try to prove some recursive bounds, which seemed very obvious. Like we figured out like what sort of recursive bounds we should prove on this function. But then even the basic recursion, the induction step, required us to use some probabilistic method. We couldn't just do it directly. It was not some very obvious thing. We had to do some sort of a projection. And for that projection, we picked like random directions. We couldn't just pick a nice direction to project into. And all of those techniques seem to only work when your grid is the full space. In fact, in our paper, we solve many problems where, for example, instead of a hyperplane, you might even have like a smaller subspace, and you can cover using that. Because our techniques are not based on polynomials, but based on these combinatorial arguments, they generalize very easily to other geometrical objects. Whereas the polynomial method stuff seems to only work for hyperplanes. And that's an open problem I will mention later. So that's the rough idea of what we do. Yeah, I didn't want to talk too much about this. It's like slightly old, but that's the idea. This is misleading. It's 23 is misleading. Okay, good. So moving on. Well, maybe before moving on. So all of this seems to suggest that the Ball-Serra bound that we discussed here is perhaps not tight in general, right? As in, it's tight in some special cases when k is 1 and k is 2 and this binary grid. And then even like in general, it's conjectured not to be tight. And it is shown not to be tight here. And then we show that it's really far away from being tight in this case. So how good is this bound? Can we actually improve it in general? Perhaps there is a more clever polynomial method argument that can improve the bound. And in our recent work, we show that's not the case. So we do show that for every grid, for every k, and every grid where one of the sets, one of the sides of the grid is large enough, and I will describe what that large enough is. In that case, we show that the Ball-Serra bound is indeed tight. So the behavior is that once your grid is kind of equalish or when more compact, so for example, the binary grid where every side is the same, in that case, Ball-Serra is perhaps not tight, but in general, when your A1 is large enough, it's always going to be tight. In fact, you can replace this real field by any field that also has enough elements. So the field should be large enough. So that's a very general construction that we give in our paper. And this large enough we determine precisely for dimension 2. Like we determine the exact threshold where this works. But for higher dimensions, we left it as an open problem. And recently, there was this Polymath Junior project where organized by Adam. So here's a plug-in for plug for Adam's Polymath Junior REU. And there, one of the students, Shreya Srivastav, she showed that our construction generalizes very nicely to every dimension. Right? So she says, she determines the exact threshold, which is what we believe should be the truth. It says that whenever your A1, so the first side, the largest side, is at least k minus 1 times the second largest side minus 1 plus 1. So just think of it as k times the second largest side. In this case, your Ball-Serra bound is always going to be tight. And yeah, it's always fun to see nice results come out of that problem. Yeah, I was very excited this year. There were many, many nice results. It was a lot of fun. Yeah. Okay, so this seems to be the correct threshold where Ball-Serra becomes tight, as if we don't have a proof of that, but we do indicate that somehow. And one of the results we prove is the following. In our paper, we show that if you are even one below that threshold, if your A1 is, the inequalities seem to be wrong here. Yeah, this should be greater than equal to, this should also be greater than equal to. So we are saying that if, okay, just going back. So when A1, the size of the largest thing is large enough, then we know Ball-Serra is tight. And what we show is that if this A1 is strictly smaller than this right-hand side, right? So imagine these should be corrected. These should be greater than equal to. In that case, for almost all grids, not for every grid, but for almost all grids, we prove that the Ball-Serra bound is not tight. Okay, so one might ask, what do we mean by almost all grids? Can anyone suggest what will be a reasonable definition here? Because maybe our definition is not reasonable, right? So I'm also looking for new ideas. What do you think could seem like almost all grids? What could we mean here? Yeah, there are hardly like 3-4 slides left, so it's okay. We can wait. Okay, nothing. Cool. So what we do prove is, in fact, okay, what we mean here is that we pick these AIs randomly. So let's say we have 0 to 1 as your range, and within that range, you pick random points, say, m points, and then you pick random n points, and then you take that grid. So a generic grid, if you want. Because the highly structured grids will be very special examples. And the way we prove this result, so now I get into some proofs, is not by polynomial method, but by using linear programming techniques. So here is the general formulation of this covering problem as a linear program. And I'll go through this slowly. So let's say we have our grid of points and we have our positive integer. And let's say this covering number is the minimum number of lines, in this case, lines required to cover while skipping one point. Then this covering number is in fact the solution of the following integer linear program. We consider the set of all lines that meet our grid in at least 2 points. Because if a line meets our grid in only 1 point, you can skip, you can ignore that. Right? From any optimal cover, you can ignore lines that meet your grid in only 1 point because you can always replace it with another line that meets the grid in at least 2 points without changing any covering properties. So then we focus on this finite set of lines, all lines meeting the grid in at least 2 points. For each of these lines, we have an integer variable which denotes the multiplicity, like how many times do you pick that line. And then we are trying to minimize the sum of these multiplicities, subject to the constraint that each point of the grid, except for the origin, each point is covered at least k times. Okay, so it's a very natural integer linear program. And now what you can do is you can, for example, divide all of these equations by k. So replace z of L by some u of L, which is z of L divided by k. Then you can do a linear programming relaxation. So you can ignore this condition of them being integers, just think of them as real numbers. Try to solve that linear program. And that gives you bounds, that gives you lower bounds on your integer linear program. Okay, so that's the main idea we use. You can do it computationally if you want, but theoretically also you can use this linear programming approach. And so by LP relaxation and using the duality of linear programming, what we can show is that the covering number is always at least k times the solution of the following dual linear program. So in the original linear program, your constraints were with respect to these points of the grid, and those become variables now, and the lines will become your constraint. Okay, that's what it does. So in the dual linear program, we are trying to maximize something. We are maximizing the weights of each point. So you pick weights on each point, you maximize it with respect to the following constraint, that if you pick any line from your collection L, then the sum of weights on those of the points on that line, points of the grid on that line, should be at most 1. That's it. That's the main constraint that we have. So if you can solve this dual linear program, then it gives you very nice lower bounds on the original combinatorial or geometrical problem. In fact, any feasible solution of this dual linear program gives you a lower bound. So now all you have to do is come up with some, in a clever way, come up with these weights, right? Find some nice weightings of the points of your grid based on some intuitions or also computer experiments if you want, and use that to prove lower bounds on your problem. And this approach generalizes quite nicely. Okay, so using this, let me show you the result that I claimed. That say now A cross B is a generic grid. So just by picking points randomly. And then let's say it looks like this. What does it mean for a grid to be generic? So let's say this is a 4x3 grid. Why is it generic? Because if I take any line joining a point on the x-axis and a point on the y-axis, then it will miss all the points in the middle. So if I take, for example, the line joining this, can you see my arrow, by the way? I've been using my arrow quite a lot. Yeah. Okay. So if I take the line joining this point over here and this point here, then it should miss all the other points in the grid. That's what happens in generic. And we really need that in our argument. Okay, so say we start with a generic grid, then we can give the following weighting. So for every point on the x-axis, we give a uniform weight. For every point on the y-axis, we give another uniform weight. And then for every interior point, we give another weight. And this has been chosen so that when you take any line in the plane, then that line meets, like the sum of weights of points of the grid on that line is at most 1. For example, if I take a vertical line, so then it will have this 1 point on the x-axis with this weight. And it will have at most b minus 1 points. In fact, exactly b minus 1 points of that weight. So if you sum this number, plus b minus 1 times that number, it's exactly equal to 1. Similarly, you can check for all lines. And hence, this gives you the required lower bound. So it shows that the covering number is at least this number here, which is the sum of all weights multiplied by k. And this lower bound is strictly better than the Ball-Serra polynomial method lower bound, exactly when you have these inequalities. And that's something you can just show computationally. So in fact, as your grid keeps getting like equal size, so shorter in that direction, then your Ball-Serra bound keeps getting worse. That's what we show. That's the intuition, at least. But note that we prove it only for generic grids. We don't prove it for every grid. So we still don't know whether that threshold is the right point for every grid. We don't know. Okay, so here's another very cool result. This is in fact the problem we really started with, because that's the first thing you would want to prove. When you're looking at just 2-dimension plane, you will probably just start with the standard grid, right? So this is 0, 1 up to m minus 1 squared. And this is a very, very nice structured grid. It's not generic in any way whatsoever. And in this case, we couldn't resolve the problem, but we could prove some interesting lower and upper bounds by similar linear programming arguments, by some sort of clever weightings and so on. And the bounds look funny. So have a look here. You have a square root 2 in the upper bound times k times m minus 1 and a 2 minus this thing, 1 over square root of e in the lower bound. There's still a gap here. And we would really like to solve that. And in fact, we conjecture that the upper bound is tight here, because that's what our computations also show. In fact, we can prove that if you're only allowed to use horizontal, vertical, or diagonal lines, then this is indeed the optimal answer. But we can't prove that in any, that's the only thing you're allowed, right? But we couldn't solve it. So these are the best bounds we could prove. I'll be very happy if any one of you improves these bounds.
What does it mean diagonal in this case? Because everything that touches 2 points can be thought of as diagonal.
That's true. So that's a good point. We meant what I meant to say is slope minus 1. Yeah. So if you only use vertical, horizontal, or slope minus 1 lines, in that case, we can prove the square root 2 bound. Yeah. Thanks for pointing that out. And with the computer, we could check for many values that you can always find an optimal cover using slope minus 1 horizontal and vertical lines. So it seems reasonable to us, at least, that this should be the correct bound, but we don't know how to improve the lower. Okay. Yeah, that's almost it. So now let me just conclude with some open problems. So firstly, of course, I would like to solve this binary grid problem, where the conjecture is that the answer should be n plus k choose 2, whereas the lower bound is n plus 2k minus 3. And with the polynomial method, at least in the obvious way, we can't improve the lower bound. That's what Sauermann and Winters will show. Maybe you can use some other properties of these polynomials to have some improvements there. Now, please solve this very easy example. This was sort of a toy case that we started with. This is how my project started here. We were like, yeah, this should be the easiest thing. Somehow this standard grid turned out to be the hardest case. Like we can solve it for almost all grids, except for these nicely structured grids. Okay, so if you can improve the lower bound, that will be great, or prove our conjecture wrong, that would be even better. And then here's a problem I'm really excited about, which is like a more theoretical understanding of these methods and these problems. So can you find a finite grid? And here I'm focusing on characteristic zero fields, let's say R, where the polynomial version of the problem has a different answer than the hyperplane version. So it's conjectured that it is true for this binary grid, but perhaps there's an easier example you can find, maybe already in the plane. And in the plane, can you find a concrete, even small finite grid, where you can find perhaps a very complicated looking polynomial, a degree 100 curve, which has the right properties, but you can't find 100 lines. So there is a separation. In fact, I don't even know any example, forget over R, over any field. I don't know any example where the Ball-Serra bound is tight for polynomials, but it's not tight for hyperplanes. So this is like a very general problem in this direction of trying to understand this polynomial method. Okay, and another very exciting open problem is what happens if you replace hyperplanes with smaller dimensional affine subspaces. So for example, in 3 dimensions, if you want to cover your grid with lines, this is really hard in general, because our polynomial method, if you remember the proof from the first few slides, required us to have these degree 1 equations defining the hyperplanes which you multiply together. And now it seems quite tricky. What's the best way to capture a smaller dimensional affine subspace here? So I don't know any nice polynomial method bounds here. And I think this will require some genuinely new ideas in this area. Okay, that's it. Thank you.
Very nice talk. Thank you very much.
Yeah.
Very interesting. So questions?
Let me start with a very simple question. So you said that there is a special point in the grid that you're trying to miss. Could it possibly matter which point you want to miss?
It does matter. So for multiplicity 1, it does not matter. But in higher multiplicities, it can matter. If your point is on the corner, that can be different. That can be a different case compared to your point being in the center. In fact, in our paper, we give some small examples where the answer is different. But we don't understand the general behavior so nicely. So it can matter for the multiplicity version, not for the classical version. Yeah, that's a good point.
I see. Thank you.
Yeah.
Anything interesting happens, just to follow up, if each cover misses a different point, which is entirely trivial?
What do you mean? Like it misses 2 points? Is that what you're asking?
No. I can partition the cover into subset, each one misses a different point. Or you can generate case.
Yeah, I'm not sure what's interesting there. Like if your hyperplanes are allowed to miss different points, you can probably just. I mean, like every hyperplane misses some point, right? The grid is not contained in a hyperplane. So, yeah, I'm not sure what's the interesting variation in that direction. Yeah, I'm not sure.
So as was hinted in the previous question, supposing you exclude more than 1 point, let's say 2 points that are some sense far away from each other in the grid.
Yeah. So when you remove only 2 or 3 points, then, or say a small number of points, then the answer is known. And this was, I can link the paper in the chat if I find it soon, by Carla Kronland and some other co-authors. And then there was a question asked by Noga Alon saying that, okay, what's the worst behavior that you can get? Like, what's the worst subset you can find of, let's say, the binary grid that's really hard to cover? Right? So when you remove only 2, 3 points, you can always do it with n plus 1, n minus 1, and whatever, something like that, something linear. But can you find some subsets of the binary grid which are terribly hard to cover, where you're supposed to miss everything outside that set? That's critical. And then it was shown in the same paper, which I will try to find and link now, that sometimes you need exponentially many hyperplanes. So using the probabilistic method, they could show that there are in fact subsets of the binary grid which require 2 to the n divided by n squared many hyperplanes. So that's really a lot. That was not the intuition initially, at least. But that's a surprising result. But there also, we don't know the exact maximum. So there's still some missing there. Let me try to quickly find that paper. But that's a great question. Give me a second. Yeah, here. So it's in the chat. I have linked the paper that tries to study this problem where instead of missing 1 point, you miss some larger subset.
So maybe again, this is silly. Does it make any sense to look at things like, at least in the plane, triangular grids and covering those with lines with excluded points or other rules?
It makes a lot of sense. So that's one of the projects we did in the Polymath Junior program, or that's one of the projects I suggested because it's already non-trivial there. But then while we were working on this, there was a paper that just appeared last month on Archive that studied exactly these triangular grids. And there, in fact, even if you don't exclude a point, just covering every point at least k times, I think that's already an interesting problem there in triangular grids. So yes, it has been studied. I can give that reference as well. This one.
I would like to ask about the the relation between Euclidean hyperplanes and hyperplanes over F2, because I was apparently on the naive assumption that if you have a Euclidean hyperplane, then the corresponding hyperplane over F2, it will cover even more because
it does cover more. It
because
does,
it covers exactly half of the.
Yes, it does. Yeah. So that's the right intuition, but still somehow it's still if you want to cover everything at least k times, somehow the finite field version of the problem, which was here, is much harder, or at least you require many more.
Yeah.
So yeah, that intuition is absolutely correct. So I was also surprised by this bound. But yeah, that's how it works sometimes.
So the intuition is not correct. So then there are
No,
Euclidean
it does.
hyperplanes.
Okay. Well, what do you mean? Like there are Euclidean hyperplanes where the coefficients are not rational, for example, or not integer. Then you can't do anything.
Rational, you can assume, I suppose.
Yeah. So if you assume rational, then yes, the binary version of that will cover half of the grid. So that's still correct. The intuition is correct. But that doesn't translate to a k cover.
But then how could you need more?
Because you
have
can
two
sometimes.
hyperplanes.
I see. So the reason is that because some of those real hyperplanes, when you work over the finite field, they will cover the origin. You still have to miss the origin.
Oh.
Right? They will wrap around, sort of.
Okay. That's the problem. Okay.
Yeah. So for example, sum of xi equal to 1. No, not that one, probably. Yeah, that's okay. But some other hyperplanes, yeah. They will cover it. Yeah. Yeah. Yeah, that's where it goes.
Sum of xi equals to 2.
Yeah, sum of xi equals 2. Exactly. Yeah. Nice. That's a good question. Yeah.